OCCRG, Optimal Cognitive Core for Faithful Question Answering. OCC Team. https://huggingface.co/occ-ai c https://github.com/optimal-cognitive-core. Abstract. Recent progress in the development of language models has been defined by scale, with each generation absorbing more of the world's knowledge into its weights. However, many practical applications benefit more from robust reasoning than from extensive parametric knowledge. In this setting, task-specialized small language models, SLMs, offer a principled design choice. We introduce Optimal Cognitive Core, OCC, a family of SLMs built around this premise. As a variant of OCC, we present OCCRAG, optimized for faithful question answering, QA, grounded in the provided context. This task directly aligns with the OCC design approach, requiring multi-hop reasoning over supplied passages while ignoring memorized knowledge. To train OCCRAG, we implement a novel pipeline for synthesizing multi-context, multi-hop QA data at scale, producing a corpus of over 3 million examples targeting multi-hop reasoning, strict context faithfulness, and calibrated abstention. We release OCC RG0. 6B and OCC RG 1.7B, both mid-trained on this corpus. The models produce structured reasoning traces with source citations grounded in literal quotes from the context. Through OCCRAG, we demonstrate that compact, task-specialized SLMs can match or exceed general-purpose models 2-6 times their size across multi-hop reasoning, hot-pot QA, musique, TEAT QA, faithfulness, confi QA, and refusal, MUSIKN, benchmarks. 1. Introduction. Frontier language models grow larger and absorb ever more of the world's knowledge, yet many practical applications benefit more from compact, task-specialized architectures. Small language models, SLMs, have demonstrated competitive or superior performance across common-sense reasoning, mathematical reasoning, tool calling, and retrieval-augmented generation, Schick and Schutze, 2021. Furthermore, fine-tuning SLMs on targeted datasets enables cost-effective adaptation to specialized use cases, an advantage especially pronounced when computational resources are limited. One such task is context question answering, context QA, where models answer questions based exclusively on a provided context, generating responses grounded in or reasoning from that input. Radevsky et al., 2025, Oshev et al., 2025. A central requirement for such systems is faithfulness, producing outputs strictly derived from the given context while disregarding parametric knowledge. Faithfulness thus measures both the alignment of the Figure 1. Performance efficiency trade-off across language models for faithful context QA. OCCRAG models 0.6b and 1.7b achieve competitive or superior performance on multi-hop reasoning, faithfulness, and refusal benchmarks compared to general-purpose models 2-6 times their size, demonstrating that a compact, task-specialized architecture can outperform larger models when explicitly trained for context grounding and evidence-based reasoning. Answer with the evidence and the absence of hallucinated content. Pledanov et al., 2025, Krako et al., 2025, Rykov et al., 2025. Context QA poses a significant challenge, as LLMs have been shown to favor their own parametric knowledge over provided context. Furthermore, even the most capable models frequently fail to remain faithful across counterfactual, inconsistent, and unanswerable scenarios. Ming et al., 2025, Bai et al., 2025. In this work, we introduce Optimal Cognitive Core, OCC, our family of SLMs that prioritizes task-specific reasoning capabilities over knowledge capacity. Within the OCC family, we present OCCRAG, to the power 1, designed for faithful context QA. The model is built around the 3 capabilities that define a strong context QA system. 1. Multi-hop inference and common-sense reasoning. to synthesize information across disparate parts of the context and bridge logical gaps with implicit world knowledge. 2. Avoidance of memorization, so that pre-training knowledge does not override or interfere with the provided context, Figure 2. And 3. Safe abstention, declining to answer when the context is insufficient, ambiguous, or lacks the necessary information to construct a faithful response. Together, these properties make OCCRAG a strong context-grounded reasoner that is both computationally practical and operationally trustworthy. We release OCCRG 0.6b and OCCRG 1.7b, mid-trained from Quinn 3-0.6b base and Quinn 3-1.7b base, respectively, on a corpus of over 3 MQA synthetic examples produced via our novel data generation pipeline. The corpus targets multi-hop reasoning, strict context faithfulness, and calibrated abstention, spanning multi-context scenarios with distractor passages and unanswerable cases. Following PLIA's RAG. The models produce structured reasoning traces with source citations grounded in literal quotes from the context. We evaluate OCCRAG on context QA benchmarks spanning multi-hop reasoning, hot-pot QA, musique, TEAT QA, context faithfulness, confi QA, and abstention on unanswerable questions, musique. Both OCCRG 0.6b and OCCRG 1.7b outperform their Quen 3 counterparts across all datasets and exceed GEMMA 3, 1b and 4b, and SmallLM 3-3b on every benchmark. They further outperform Quen 3 models 2-6 times, larger on faithfulness, abstention, and financial reasoning, and substantially improve over the prior context QA specialized baseline, PLIA's RG 1.2b. For example, OCCRG 0.6b exceeds Quen 3-1.7b 2.8 times, larger, by 9.5 points on confi QA, Quinn 3-0.6b to 5.2, and surpasses PLIA's RG 1.2b by 21.6 points on musique. Through OCCRAG, we demonstrate that compact, task-specialized SLMs can match or exceed larger general-purpose models. Figure 2. Faithful, truthful, and hallucinated responses under context memory conflict. The context contains a counterfactual claim, de Gaulle as the first U.S. president, contradicting real-world knowledge. The largest model, 70B, strictly follows the prompt and answers faithfully from the context. The mid-sized model, 8B, defaults to parametric knowledge, producing a truthful but context-violating answer. The smallest model, 1B, hallucinates an unsupported response. In contrast, OCCRG 1.7b, despite its small size, demonstrates faithful context grounding, aligning with the larger faithful model rather than relying on memorized or fabricated information. 2 model design principles. OCCRAG models, our SLM family specifically designed for context QA, should possess the following properties. 1. Multi-hop inference and common sense reasoning for complex questions. 2. Avoidance of memorization, faithfulness to context, no conflict with internal knowledge, and 3. Safe abstention when the provided context is insufficient. Mid-training serves as a core stage that explicitly shapes the SLM's reasoning architecture for context QA, enabling developers to gain fine-grained control over evidence combination and yielding more reliable, interpretable, and context-aligned downstream QA. Large-scale agentic mid-training on synthetic trajectories across math, code, and tool use further internalizes planning and reflection, unlocking native agentic potential in lightweight models and surpassing larger baselines on agentic benchmarks. Langley et al., 2025, Team, 2025b. Mid-training enables strong multi-hop reasoning. Mid-training on reasoning trace datasets improves QA performance of SLMs by training them on the functional structure of multi-hop inference, such as sub-question decomposition, information retrieval, and stepwise verification, rather than simply teaching them to reproduce surface-level answer patterns. This structural signal helps SLMs internalize the process by which correct answers are reached, which in turn boosts generalization to new QA instances and reduces reliance on superficial shortcuts. Lee and Hockenmayer, 2025. Liang et al., 2026. Mid-training supports faithful, context-grounded, non-memorized QA mid-training on context-based reasoning traces that always tie each step back to the provided text. Ensuring strict faithfulness to evidence helps SLMs learn to solve QA tasks without memorizing facts or hallucinating. Studies on multi-hop QA show that fine-tuning alone on raw text or continual pre-training yields only limited gains, whereas structured or supervised mid-training on evidence-anchored traces substantially improves answer accuracy without relying on internal knowledge. Ren et al., 2026. Lee et al., 2024. Mid-training encourages calibrated abstention when mid-training includes context-insufficient or unanswerable examples annotated with explicit reasoning trace patterns, e.g., no evidence in context. The SLM learns to recognize when the context does not support a confident answer. This kind of structured reasoning training is shown to improve the model's ability to abstain appropriately, rather than hallucinate, on information-limited tasks and partial context environments. In effect, mid-training turns abstention into a learned reasoning behavior rather than a heuristic, making the SLM more reliable in high-stakes QA settings. Zhou et al., 2026. Wen et al., 2024. 3. Training data. This section describes the synthetic corpus used for mid-training of our context-grounded QA model. The corpus is built to exercise the 3 properties stated in Section 2, requires reasoning over the supplied context. Every answer is recoverable from the context alone to avoid memorization. And a fraction of examples carry insufficient evidence, so abstention becomes a learned response. Each training instance consists of a question, one or more golden context chunks from Wikipedia containing all supporting facts, semantically similar distractor contexts, a structured reasoning trace, and the final answer, or not enough information, for refusal cases. The corpus is built as a mix of 3 subsets of increasing difficulty, covering a broad range of questions from simple single-hop lookups to complex multi-hop fusions. Easier examples: single-hop lookup, are cheap and abundant. Harder ones, multi-hop fusion, are progressively more expensive to generate cleanly, and their volume is correspondingly smaller. See Section 3.4. 3.1 Single-hop QA generation. Single-hop questions are those that can be answered using information from a single paragraph, without requiring multi-step reasoning, aggregation, or arithmetic operations. This category represents the largest portion of the dataset, as high-quality single-hop examples are relatively inexpensive to generate at scale, and because relevance filtering remains the primary challenge in real-world deployment. The pipeline for single-hop QA generation has 4 stages: ingest and chunk page, generate QA, mine distractors, and filter. We describe each in turn. Ingesting and chunking in the English Wikipedia XML dump. Each page is run through a Wikitext cleaner that strips templates, references, infobox, and gallery markup. A page is split into paragraphs, and each paragraph becomes a candidate chunk. A chunk is precisely the unit of context the trained model sees. QA generation. For each gold paragraph, we issue a single call to GPT-OSS 120B, asking for 10 short QA pairs returned as a JSON array. It instructs the LLM that questions must be self-contained and answers must be short and extractive. Distractor mining. For every gold page, we fetch up to 1,000 child pages from the Wikipedia link graph and apply the same cleaning and chunking routine as described earlier. Every resulting child paragraph is scored against the gold paragraph by pdf cosine similarity. We keep the top 20 children by similarity. Filtration. In the final stage, an LLM as judge evaluates the generated QA pairs. This step filters out any pairs that are inaccurate or lack logical flow, ensuring only high-quality data remains. Detailed criteria are provided in Section 3.3. 3.2 Multi-hop QA generation. Multi-hop QA questions require the synthesis of multiple facts rather than simple span extraction from a single sentence. To ensure that questions remain strictly grounded in the provided evidence, we condition its generation on a knowledge graph, KG, extracted from the context, gold, and distractor chunks, requiring the LLM to follow an explicit reasoning path sampled from the KG. We employ this KG condition pipeline to address three fundamental limitations that arise when attempting to generate multi-hop questions using the same approach as for single-hop QA. Lack of structural support. Many passages contain sufficient fact density for single-hop questions, but lack the bridge entities necessary for multi-hop reasoning. Our approach resolves this by sampling reasoning paths directly from the KG, which guarantees the existence of such bridges. Verification complexity. Questions that are complex to answer are often equally difficult to verify, as a generated question may be valid while the LLM's answer to it is not. By conditioning generation on a specific path, the gold answer is fixed by the path itself rather than being subject to the generator's output. Lack of structural control. Free-form generation often results in questions with unknown reasoning structures, making it impossible to analyze or balance the corpus by question type. In contrast, sampling chains from the KG provides full control over the structural and compositional complexity of the generated dataset. 3.2.1 Knowledge Graph Extraction. We extract gold paragraphs and their associated distractors from the training split of the musique dataset. To achieve fine-grained control over automatic question generation, we employ the knowledge graph, KG, extraction pipeline introduced in Wakantic. This pipeline transforms unstructured text into a structured factual graph, which serves as the backbone for our controlled multi-hop QA generation. Wakantic employs ontological constraints from Wikidata to eliminate redundant and inconsistent information and performs entity normalization and deduplication to maximize graph connectivity. We utilize GPT-OSS 120B as the base model for Wakantic. The extracted KGs are then stored in an RDF database, facilitating efficient structural queries and subgraph retrieval. This representation allows us to explicitly select subgraphs based on predefined topological properties, such as path length, branching factor, and relation types, providing precise control over the reasoning complexity of our generated multi-hop questions. 3.2.2 Path sampling and question types. To control the complexity of the generated data, we adopt the question taxonomy of the Dragon benchmark. Specifically, we generate simple questions, 3 families of 2-hop questions, set, multi-hop, and condition, and 3-hop bamboo-style questions. Each type corresponds to a separate SBRQL template that selects a subgraph of a given shape and rejects degenerate cases via additional filters. For every sampled path, the LLM receives a short, type-specific prompt that specifies 1. The reasoning structure, 2. The gold path, 3. The supporting paragraphs, and 4. Hard requirements on the output. The question must be self-contained. The answer must be a literal span of the supplied context, and the answer must be reachable only by following the path. For every sampled path, we issue a single call to GPT-OSS 120B with the type-specific prompt to generate a QA pair. 3.2.3 Unanswerable question construction. A fraction of our corpus includes refusal examples, where the model should abstain when the provided evidence is insufficient. To generate these hard refusal cases, we use a DBERTA model fine-tuned on Squad to answer questions using reduced subsets of the original gold contexts. If the predicted answer does not match the original one, the model should abstain. The intuition is that if a strong extractive model cannot recover the answer, a critical piece of information is missing, even though relevant evidence remains in the context. Figure 3. Structure of OCC or AG output. The model proceeds through 3 named sections. Query analysis identifies what the question asks and the entities involved. Source analysis attributes relevant facts to specific source passages, and reasoning combines them to derive the answer. This structure keeps every conclusion tied to the supplied context and yields a calibrated answerable/unanswerable status alongside the final answer. 3.3 Structured reasoning. To make the three target behaviors of Section 2, multi-hop inference, evidence grounding, and calibrated abstention, learnable from token-level supervision rather than left implicit, we enrich every QA pair in the corpus with an explicit reasoning trace. The trace structure is illustrated in Figure 3 and described in detail below. A sample of the prompt/response format can be found in Figure 6, Appendix A. Reasoning format: we adopt the trace format of PLIA's RAG, in which the reasoning is laid out as a sequence of named sections. The first section, query analysis, describes what the question asks and which entities and relations are involved. The second, source analysis, identifies which of the supplied sources are relevant and what each one contributes. The third, reasoning, shows how the relevant facts are combined into the final answer. A closing answer section carries the answer string. To this scaffold, we add a status section that emits an explicit answerable/unanswerable verdict immediately before the final answer. The addition is motivated by our refusal objective, turning abstention into a discrete label that the model has to commit to before producing the answer makes the decision boundary between answerable and unanswerable cases an explicit supervised target, rather than something the model has to infer from the wording of the answer alone. Generation: we generate reasoning traces using Qwen 3.5-27b. For sampling parameters, we use the values recommended in the original model card to the power 2. We disable thinking mode during generation for two reasons. First, enabling Qwen's native thinking adds substantial generation cost, as the model emits an additional internal trace before producing the structured output. Second, on our development slice, this extra native reasoning did not yield a meaningful improvement in distilled student quality. We emphasize that this concerns only the model's built-in thinking mode, as the structured reasoning trace emitted in our own format, described above, is exactly the supervision signal we want the student to learn and is always present in every generation. Qwen 3.5-27b was itself selected over other open-weight generators by distilled student performance on a held-out development slice covering every question type and both answerable and refusal cases. Filtering: each generated trace passes through 4 checks. 1. Format: we check that all the fields query analysis, source analysis, reasoning, status, answer are preserved. Traces with a missing section are dropped. 2. Answer match: the predicted answer is compared to the gold answer by exact match. On answerable examples, a mismatch causes the trace to be dropped, and on refusal examples, any trace that asserts a non-refusal answer is dropped as well. 3. LLM as a judge: examples that fail exact match are then rechecked by Qwen 3-4b, prompted as a verifier, which compares the predicted answer against the gold. Traces the judge does not endorse are dropped. 4. Overthinking: as noted above, Qwen 3.5-27b is prone to overthinking, producing long reasoning chains on questions that admit a short solution. We filter these in 2 stages. First, we drop any trace whose reasoning section exceeds 1,256 tokens. Second, we drop any trace containing more than 10 thinking markers such as weight and alternatively, which we collected manually by inspecting the long tail of the trace length distribution. 3.4 Dataset statistics: the final corpus contains approximately 3.25 m QA pairs, which include 2.78 m single-hop pairs, 262 k multi-hop single-context pairs answered within a single passage, 165 k multi-hop multi-context pairs requiring cross-passage information fusion, and 43 k abstain pairs where no passage supports the answer. In total, the dataset encompasses roughly 8 Qwen 3 tokens, where the single-hop subset dominates the overall budget, 7.76 B tokens. Across the corpus, distractor contexts consume the largest share of tokens, 35% minus 75%, followed by gold contexts and reasoning chains, see Figure 4. Figure 4. Training token budget by subset. Left. Total Qwen 3 tokens per subset on a logarithmic scale. Right. Per subset decomposition with distractor context, gold context, reasoning. For mid-training. This section describes the mid-training procedure. We do not pre-train our own model from scratch, but start from an existing pre-trained base model. We further mid-train it on the synthetic data introduced in Section 3. Base model, we compared 3 open-weight families of small language models as starting points: Qwen 3, Gemma 3, and Small LM 3. Selection was based on early runs evaluated on a held-out QA slice. Qwen 3 produced the strongest result at fixed compute and was retained for both release sizes. Our final checkpoints are obtained by mid-training Qwen 3-0.6b base and Qwen 3-1.7b base. Training objective and format, we train via supervised fine-tuning, with the loss applied only to the response tokens. The complete prompt/response format is shown in Figure 6, Appendix A. The prompt is a question together with the context passages in random order, each tagged with a numeric source identifier. This format is identical to the format used at evaluation time, so no train-test mismatch is introduced. The response is a reasoning trace, generated and formatted as described in Section 3.3. Note that the final answer and the answerable/unanswerable verdict are included in the reasoning trace. To make boundaries between prompt elements, query, context passages, and response sections, query analysis, source analysis, etc., explicit, we delimit them by a small set of additional special tokens. Their embeddings are added to the base model and initialized from the mean of the sub-word embeddings of their natural language names. Data mixing as described in Section 3. Our training corpus contains 3 main subsets: 1. Single hop, 2. Multi-hop single context, and 3. Multi-hop multi-context. The single-hop subset is roughly an order of magnitude larger than each of the multi-hop subsets, but multi-hop examples are the ones that actually exercise the reasoning capability we want the model to develop. We therefore oversample both multi-hop subsets. Each multi-hop example is shown 3 times within a single epoch, while every single-hop example is shown once. This consistently improves multi-hop benchmark accuracy without measurable regression on single-hop. We also evaluated a curriculum schedule that trains only on single-hop examples at the beginning and starts mixing in multi-hop data from a fixed step onwards, but observed no measurable difference compared to the static mixture. Implementation details: OCC RG 0.6b and OCC RG 1.7b were both trained on approximately 9 by 10 to the power 9 tokens, respectively, taking approximately 17 and 28 wall clock hours each on 8 NVIDIA H100 80GB GPUs. Full training hyperparameters and the distributed training configuration are listed in Appendix B. 5. Evaluation. Figure 5. Multi-dimension general comparison of OCC RAG versus different models. OCC RG 0.6b and OCC RG 1.7b show balanced profile, outperforming competitors, 2-3 times larger. For Qwen 3 and Small LM 3, we report results with thinking mode on. Table 1. Evaluation benchmarks, the number of evaluation samples and supplied sources, the task each one tests, and the metric we report. Confi QA is evaluated on its 3 subsets: QA, MR, MC. On TTQA, we keep only span and multi-span questions. 5.1 Benchmarks. We evaluate the models across 3 core dimensions summarized in Table 1: multi-hop reasoning, faithfulness, and refusal. Multi-hop reasoning: to assess the core capability of a context QA model, we utilize 4 benchmarks spanning multiple domains: Hotpot QA and Musique for Wikipedia-based multi-hop QA, and TTQA for table-grounded multi-hop QA in finance. Hotpot QA and Musique both pair gold supporting sources with distractors. We fix the total number of sources supplied to 10 in these datasets. TTQA provides 4 question types: span, multi-span, arithmetic, and counting. We restrict evaluation to the first 2 and exclude the latter 2, which conflate retrieval with numerical computation and therefore fall outside the context-grounded QA capability we aim to measure. We report inaccuracy. In ACC, i.e., the gold answer appears as a substring of the prediction on Hotpot QA and Musique. For TTQA, We report F1 token level overlap between prediction and gold answer. Faithfulness to the provided context is evaluated using ConfiQA. ConfiQA pairs each question with a counterfactual context built from chains of Wikidata triples and comprises three subsets of increasing difficulty: QA, a single triple with a counterfactual tail, MR, a multi-hop chain with one counterfactual triple, and MC, a multi-hop chain with every triple replaced. We report an ACC against the counterfactual gold answer together with the memorization ratio, M subscript R, which measures how often the model defaults to its parametric knowledge when it conflicts with the supplied context. Formally, M subscript R equals P subscript O slash P subscript O plus P subscript C, where P subscript O is the rate at which the model produces the original, memorized, answer, and P subscript C is the rate at which it produces the counterfactual, context-grounded, answer. Lower values indicate stronger context adherence. Refusal: the ability of the model to decline to respond when evidence is insufficient is evaluated using MuSiKN. It is the unanswerable counterpart of MuSiK, in which the supporting passages are replaced so that no extractive answer remains in the context. We fix the number of input sources to 10. We instruct the model to output the phrase, "not enough information," when the context does not support an answer, and report refusal accuracy, RCC, as the fraction of predictions that contain it. We compare against open-weight model families Qwen3, Gemma3, SmallLM3, and Pliaz-RAG, taking all available checkpoints up to 32B parameters. This broad range allows us to assess whether a task-specialized SLM can close the performance gap with general-purpose models by an order of magnitude larger. For all of these models, we use sampling parameters as recommended in the corresponding technical reports. Qwen3 and SmallLM3 models support both non-thinking and thinking modes. We report both. As we discussed in previous sections, OCCRAG generates compact reasoning traces that provide source citations with literal quotes from the context, achieving chain-of-thought level transparency at a fraction of the cost of full thinking mode inference. 5.2 results. Although 2-6 times smaller, OCCRAG models achieve competitive or superior performance relative to models up to 4B parameters, Figure 5. OCCRAG 0.6b at just 0.6b parameters exceeds Gemma 3-4b and SmallLM 3-3b on each dimension. OCCRAG 1.7b further closes the gap with Qwen 3-4b in thinking mode on multi-hop reasoning while achieving the highest results on faithfulness and refusal. The gap with Pliaz-RAG 1.2b, the most directly task-comparable baseline, is particularly pronounced on multi-hop reasoning benchmarks. We attribute this to the multi-hop training data that our generation pipeline provides, and which, as can be inferred from their technical report, Pliaz-RAG's generation process does not include. Our final evaluation extends the comparison across the full Qwen3 and Gemma3 families up to 32B parameters, Table 2. While models at 8B and above retain a lead on multi-hop reasoning, the distance to OCCRAG is substantially narrower than the gap these same models hold over their instruct-tuned counterparts at equivalent scale. Importantly, both OCCRAG models achieve the best faithfulness performance across all evaluated scales, attaining the highest ConfiQA accuracy and the lowest memorization ratio. Our mid-training reduces M subscript R from 12.7 8.3 Qwen 3-1.7b to 5.0 OCCRAG 1.7b, demonstrating that the model has learned to prioritize the provided context over its parametric knowledge. The same pattern holds for refusal, where OCCRAG 1.7b attains 87.2 RCC, on par with models of 8B parameters or higher. Table 2. Main evaluation results. ConfiQA metrics are averaged across QA, MR, and MC subsets. Parentheses, if available, represent the evaluation results with thinking mode on. We highlight the best result per column as bold and second best as underline. 6. Conclusion. We presented OCCRG, a family of small language models designed for faithful context-grounded question answering. By combining large-scale synthetic mid-training, explicit reasoning traces, and citation-aware output formatting, OCCRG learns to answer only from the provided context and to abstain when evidence is insufficient. Across multi-hop reasoning, faithfulness, and refusal benchmarks, the released 0.6b and 1.7b checkpoints consistently outperform stronger baselines under 4b parameters and remain competitive with much larger models, while using substantially less compute. A key takeaway from this work is that faithfulness does not require scale alone. It can be learned through the right training curriculum and supervision format. In particular, our synthetic corpus shows that multi-hop reasoning, context grounding, and calibrated abstention can be jointly trained in small models without sacrificing efficiency. The results suggest that an optimal cognitive core is a practical alternative to ever larger general-purpose models for applications where correctness must be tied to evidence. More broadly, OCCRG provides a reusable recipe for building compact QA systems that are transparent, efficient, and robust to missing or conflicting evidence. We hope this work encourages further research on structured mid-training, evidence-anchored reasoning traces, and faithful abstention in small language models. 7 acknowledgements. We would like to thank Victoria Chekalina, Victoria Dochkina, Yana Kulichenko, Andrei Kuznetsov, Maxim Kirkin, Gleb Kuzmin, Ruslan Kostoev, Sergei Pledanev, and Valery Ternovsky for their insightful comments. OCCRG prompt/response example. Prompt. Response. Figure 6. Example of the prompt/response format used at mid-training and at evaluation. The prompt wraps the question in query, tokens, and each context passage in source, tokens prefixed by a numeric source_ID. The response is split into 5 sections delimited by asterisk operator, tokens. Reasoning composes evidence from sources 1 and 3 into a 3-hop chain. Karen Hayes, 24, Jack Bauer CU. Status carries the discrete refusal verdict, and answer carries the final span. The example is taken from the multi-hop, multi-context subset of the training corpus. B. Mid-training hyperparameters. Table 3. Mid-training hyperparameters for the released OCCRG checkpoints. To the power 1 asterisk operator, core contributors. To the power 2, correspondence to ivan.osladets@gmail.com. To the power 1, we name our models OCCRG to emphasize their specialized optimization for retrieval-augmented generation, RAG, pipelines, even though they embed no explicit retrieval component. This naming follows established conventions in faithful QA systems, e.g., PLIA's RAG, where the suffix signals the model's primary deployment context and evaluation setting rather than internal architecture. To the power 2, https://hf.co/qn/qn3.5-27b.